Hi, everyone. So in previous sessions, we've talked a lot about how to measure different kinds of quantities of things in astronomy, how to measure distances, how to measure speeds. And in this session, we're going to apply that to making measurements of different galaxies and then looking for patterns in that data that give us tools to study new aspects of the universe around us. So we're going to be specifically looking at some of the properties of galaxies, and like in any other kind of science, if we gather a whole bunch of data, we want to try to find patterns in that data that allow us to study some new kind of phenomenon. So let's talk about these galaxies a little bit. So in previous sessions, we've talked about the spectras of galaxies. We said for spiral galaxies, we have these emission spectra where we have these strong hydrogen lines owing to those ionization nebulas, those areas that are right by those O and B stars that are exciting those gases, causing them to glow with those characteristic emission lines. We get these emission spectra for galaxies. When we looked at elliptical galaxies, their spectras were more absorption spectras, showing the absorption property of some of those older types of stars that are dominant in these elliptical galaxies. For irregular galaxies, again, we have these emission spectra owing to those ionization nebulas. So in all of these cases, we can identify different spectral lines associated with different elements in those galaxies. What we want to do is combine those measurements of these spectras with this Doppler shift idea. We talked about the Doppler shift earlier in the course, where if I measure how red shifted or how blue shifted some light is, then we can identify how fast that galaxy is moving or how fast that object is moving. And the equation that we had was the speed of the object, the speed away from us. So if it's away, it's going to be positive. If it's towards us, it's going to be negative, is equal to the shifted wavelength. And this is what we actually see in the spectrum. So this is what we observe in spectrum of moving object. So that shifted wavelength minus the rest wavelength, this is what we observe from element in a lab. Divided by the rest wavelength. And then all of that multiplied by the speed of light. And for these calculations, we're going to look at the speed of these speeds specifically in kilometers per second. So for the speed of light, we can use 3 times 10 to the 5 kilometers per second. So again, for this Doppler shift equation, we can divide both sides by c if we want. We have that radial velocity in kilometers per second. We have the speed of light, 3 times 10 to the 5 kilometers per second. This shifted wavelength is when we look at the spectrum of some distant object that may be moving, when we look at the spectrum of that moving object, where do we find these particular wavelengths, the wavelengths of these particular kinds of elements? And the rest wavelength is if we were to observe that particular kind of element, say hydrogen, in the lab, when we observe hydrogen in the lab, what are the wavelengths that are going to be emitted? So we can use this Doppler shift to figure out that radial velocity. Let's look at some examples of this. So here we have an elliptical galaxy. We have this absorption spectrum, and we can observe some of these spectral lines. So let's say we're looking specifically at this sodium absorption line, where that sodium absorption, that particular line occurs at 5,898 angstroms. So in a lab, let's kind of do this as an example. In the lab, that rest wavelength for the sodium absorption is 5,898 angstroms. If we look in this particular spectrum, well, that sodium absorption line is not showing up at 5,898 angstroms. It's showing up at a longer wavelength. That wavelength has been stretched due to that redshift effect. And where we actually seem to be identifying this is at around 6,400 angstroms. So lambda shift is 6,400 angstroms. Okay, so let's go through this Doppler shift equation and see if we can calculate how fast this galaxy is moving. So we've got the shifted wavelength of 6,400 angstroms minus the rest wavelength of 5,898 divided by that rest wavelength. I'd recommend putting brackets around that so you know that that part we're going to do first. And then we're multiplying that by the speed of light, 3 times 10 to the 5 kilometers per second. When you're going through these equations, as I've mentioned previously, I strongly recommend you do this equations in parts, first doing the subtraction for the numerator, and then doing those next steps. So let's do that equation. So if we subtract those terms in the numerator, I got 502 over 5898 times 3 times 10 to the 5. If I do that division, the 502 divided by 5898, I get 0.085 times 3 times 10 to the 5. And if I multiply those together, I get around 25,500 kilometers per second. So again, I probably should have done the third significant digit there. So put a 1 there just to have a little bit more completeness. And this term here, sometimes we refer to this as the redshift. That decimal value you get before multiplying by the speed of light. Sometimes that is referred to as the redshift, and that's denoted by a lowercase z. We're not going to worry about that one too much, talking about this redshift. Basically, we are always going to want to get to this final, how fast is the galaxy moving? So this galaxy is moving at around 25,500 kilometers per second, and that is going away from us. When you get positive values for this, that just means it's moving away. So again, the point of this one is to say, if I can identify these spectral lines, if I can look at the spectrum of this galaxy and identify some of those spectral lines, I can measure those shifted wavelengths from the graph. And then if I know at what wavelengths those spectral lines show up in the lab, then that's going to be the rest wavelength. And then I can use that information to figure out how fast this galaxy is moving. I have a bunch of examples on here. I'm thinking maybe I'll do one more, and then I'll make sure that I post the notes for some of these other ones. But let's try another one of these examples. So for this galaxy, we have this hydrogen emission line. Erase some of this stuff. Let's just erase that. So we've got this hydrogen alpha line, and that hydrogen alpha line, if we are looking at hydrogen in the lab, that wavelength shows up at 6,563 angstroms. So 6,563 angstroms. But again, we notice that on this spectrum, this hydrogen alpha line isn't showing up at 6,563. It's showing up a little bit closer to 7,510. So it's a little past 7,500 angstroms. Let's use that as our shifted wavelength, 7,510 angstroms. And once again, we can use the Doppler shift equation. So velocity is the shifted wavelength, 7510, minus the rest wavelength, 6563, over the rest wavelength, and then multiplied by the speed of light. So once again, I recommend do the subtraction first. In this case, I got 947 over 6563. And still multiplied by the speed of light. After that division, I get 0.144 times our speed of light is 3 times 10 to the 5 kilometers per second. And when I multiply those two together, I get 43,300 approximately. Just leaving that at 3 significant digits. For all of these equations, we always want to use, we're going to kind of default to 3 significant digits for all of these kinds of measurements. So once again, if I can measure that shifted wavelength from the spectrum, and if I have that reference wavelength for what that emits, what wavelengths that particular spectral line shows up at in the lab, we can use that information to figure out how fast this galaxy is moving. And again, this is away from us, it's a redshift. So again, I think I rounded slightly differently on mine, but close enough for that. We'll match those up. So again, if I want to calculate the speed of the galaxy, we identify the galaxy spectrum, identify some of those common spectral lines where we know their reference wavelengths, so we can identify at what wavelength do those show up at in the lab. We can identify the shifted wavelengths, and then we can use that Doppler shift equation to figure out the speed of the galaxy. So let's just kind of look at a couple more examples of this. I'm not going to go through the calculations myself. I'm just going to kind of start these up, and I encourage you to pause the video and try the calculations yourself and compare them against the solutions. So if I look at this hydrogen alpha line, it has a rest wavelength of 65,063. So based on this one, well, this shifted one is actually pretty small. Let's say the shifted one is at 6,700 angstroms. So pause the video here for just a moment and try to go through this Doppler shift equation to calculate how fast this particular galaxy is moving. Okay, so basically the results that you should get from this, if you do that redshift calculation, then the number that comes in front of the, just before you multiply by C, that should be 0.021. And from that, you can figure out how fast that galaxy is moving. We can do the same thing using the same galaxy, just a different spectral line. So let's use the sodium line in this case. Ordinarily, it shows up at 5,898 angstroms. In this spectrum, it's showing up just over 6,000, so let's call that 6,010 angstroms. Try to repeat the calculation and see if you get the same redshift and the same radial velocity for this galaxy. So pause the video and give that one a try. Okay, so after you go through the numbers for this one, you should get, again, at least within rounding, because when we're picking these shifted wavelengths, it's not going to be 100% accurate. It's going to be approximately accurate, but we do get approximately the same redshift. So if you kind of average out these two cases, this galaxy should be moving at around 6,000 kilometers per second. Again, this is a redshift and it's moving away from us. We can try a couple more. So again, just getting practice. If you're already good with this, then you can kind of skip ahead to the next part of the video. This hydrogen emission line ordinarily shows up at 65,063. So try to identify approximately what wavelength is this line showing up at. Let me zoom in a little bit more so hopefully you can see that one a little bit better. So try to identify what wavelength that is showing up at and calculate the speed of this galaxy. So pause the video for a minute and give that a try. Okay, so when I ran the numbers on this one, I said that shifted wavelength is around 6,900 angstroms. And when we go through the calculations, we can identify the redshift, so the change in wavelength, shifted wavelength minus the rest wavelength divided by the rest wavelength. And this galaxy seems to be moving at around 15,000 kilometers per second. Now, just to show how extreme this can get, this is the spectrum of a quasar. And when we talked about quasars, we said they're generally very, very far away. They're more common in the past, so we're seeing their light as they were in the past. On this spectrum, notice that we don't even see the hydrogen alpha line because it's been so redshifted that it's just off the side of the graph. It's now into the infrared part of the spectrum. But what we can see are some other spectral lines. This magnesium line, this particular magnesium 2 line, generally shows up in the in the ultraviolet part of the spectrum. But this thing has been so redshifted that what was in the ultraviolet part of the spectrum is now in the visible spectrum. It ordinarily shows up at 2,799 angstroms. In this shifted wavelengths, it's around 4,250 angstroms. So try to do this same redshift calculation for this example. Again, pause the video, give yourself a minute to try this calculation and see how fast this galaxy is moving. So if you look at the redshift, again, the change, the shifted wavelength minus the rest wavelength divided by the rest wavelength. In this case, you get 0.518. So this galaxy is moving at around 157,000 kilometers per second. This one is moving really, really quick. In fact, for galaxies that are moving this quick, there's actually a modified version of the Doppler shift equation that we kind of have to put into play. We're not going to worry about that for the purposes of this course. It has to do with special relativity. This equation changes a little bit as you get going really, really fast.